For all of human history, we've looked at our blue oceans, our protective atmosphere, and our steady yellow sun, and we assume this is as good as it gets. Earth is the gold standard for life. That assumption became a strict constraint. When astronomers first started searching the galaxy for signs of biology, they were looking for a mirror image of our own planet. The logic was simple. If a world didn't have a yellow sun, Earth-like gravity, and a 365-day year, it was dismissed. That narrow view of habitability held until 2009, when NASA launched a dedicated exoplanet hunter into the dark. Kepler was built with a singular, highly specific mission. It pointed its massive 96-megapixel camera at a single fixed patch of the Milky Way. It stared unblinkingly at hundreds of thousands of stars, waiting to catch a shadow. This is a chart demonstrating the transit method. When a planet crosses directly in front of its host star, the star's light dims by a fraction of a percent. Kepler's sensors were sensitive enough to detect that microscopic drop in luminosity. By measuring exactly how much the light dips and how long the shadow lasts, astronomers capture all the hard data needed to calculate the hidden planet's physical size and its orbital path. Over 9 years, Kepler confirmed over 2,600 new worlds. The data revealed gas giants known as hot Jupiters, orbiting so tightly they complete a year in a matter of days, and extreme lava planets with star-facing hemispheres made of liquid molten rock. The sheer volume of these discoveries suggests that our solar system is just one configuration among many. It reframes Earth not as the universal standard, but as a unique variant, opening the possibility that even more favorable worlds are waiting to be found. If we throw out the requirement for an Earth clone, we can treat habitability as an optimization equation. The foundation of that equation starts with the most critical variable, the host star. Our yellow sun is massive and bright, but red dwarfs are smaller, cooler, and make up over 70% of all stars in our neighborhood. Because their energy output is lower, rocky planets can orbit in tight, densely packed formations and still maintain temperatures capable of supporting liquid water. Consider the Gliese 667 system. The entire habitable zone around this faint red star fits entirely within the orbital distance of Mercury. Inside that tiny band, up to 4 rocky planets are crammed closely together. The problem with red dwarfs is their violent instability. They frequently emit intense bursts of radiation. A single flare can be 1,000 times stronger than what our sun produces, bombarding nearby planets with lethal energetic particles. To balance a stable climate with a safe radiation environment, the optimization equation requires an upgrade, an orange dwarf. Orange dwarfs, like the one hosting KOI 5715.01, have about 3/4 the mass of our sun. They burn with a gentle, steady light, lacking the destructive volatility of a red dwarf. This chart illustrates the massive temporal advantage of that calm output. A yellow sun like ours burns through its fuel in about 10 billion years. An orange dwarf can provide a steady, mild climate for 30 billion years or more. It gives alien climates an incredibly vast, unbroken timeline to stabilize. For biological life to achieve maximum complexity, it does not need the brightest star. It needs the most enduring one. The second variable is the physical size of the planet itself. The Kepler data confirms the existence of rocky planets significantly larger than our own, known as super-Earths. Exoplanets like KOI 5715.01 and Gliese 667cc have greater mass and radius. That extra surface area translates directly to more room for expansive coastal zones, shallower, nutrient-rich seas, and massive liquid networks under alien skies. A larger planet also generates stronger gravity, allowing it to pull in and hold on to a much thicker atmosphere. This heavy atmospheric envelope acts as a perfect blanket, trapping heat effectively and stabilizing the global climate against extreme fluctuations. The trade-off is the extreme environmental pressure. On a massive super-Earth, surface gravity could reach up to 1.9 g. A human standing on one of these worlds would feel nearly twice as heavy, with atmospheric weight mimicking the crushing pressure deep in Earth's oceans. If biology were to emerge under these conditions, it would face a brutal evolutionary filter. Organisms would have to adapt to physical loads that would crush terrestrial life.
leading to forms that challenge our definition of what is possible. With tight habitable zones, planets face tidal locking. One hemisphere permanently faces the sun, boiling in eternal day, while the other freezes in eternal night.
Life is forced to survive solely on the narrow border of permanent twilight between these extremes. Optimizing for habitability leads us to these extreme, radically alien environments. They suggest a reality where life's development wouldn't mirror our own, but would be dictated by physical laws we are only just beginning to map. When you calculate the final result of this optimization equation, the most habitable world is likely a massive super-Earth with deep oceans and a thick atmosphere, orbiting quietly around an ancient orange dwarf. For decades, we stared into the night sky searching for our own reflection, but the universe has no obligation to replicate Earth, and our search for biology has been restricted by our own narrow definitions. Now, observatories like the James Webb Space Telescope are utilizing Kepler's data, aiming their massive mirrors directly at these super-habitable candidates to analyze their atmospheres. It suggests that Earth is not the absolute limit of biological potential. The data reveals the ingredients for life to not just emerge, but potentially flourish across cosmically vast timescales, leaving us to wonder what might already be waiting out in the void.